The networking opportunities here at CppCon are well above and beyond any other C++ conference that I've ever been to.
Our time is precious. We only have 30 minutes. We have a lot to cover, so let's jump in. Imagine this, a new C++ programmer, newly minted, fresh out of university. They know modern C++. They know about containers. They know about algorithms. They are eager to prove themselves. They've started at their first job, and the manager brings up the backlog and says, let's choose a task. Here's the task that they select. Output the median after the samples are collected. Perhaps at this particular company, they're collecting millions, let's say 10 million samples a day of integer values. And at the end of the day, they want to know, what was the median value? That's it. Seems pretty simple. New programmer says to themselves, I bet there's an algorithm for that. So they go looking. In CPP reference, of course, they go into the algorithms library, and what do they find there? They do not find median. They do not find mode. They do not find mean. This is not going to slow them down. They're going to turn to the next best solution, and you know what it is, don't you? It's AI. ChatGPT, how do I find the median of a container in C++? You ready for it? Here's what they see. Call sort, find the middle, access with array index. Okay, I can do that. Here's the code that they write. They're pretty happy with this. They tried passing the vector by const reference initially, but they got some weird compiler errors, and so they're just passing by ref. They're calling sort, like ChatGPT told them to. They're using range-based algorithms, pretty sweet. Compiles clean, works for their test cases, so they submit for a code review. Okay, let's pause for a minute. First of all, is it unreasonable to want a median algorithm? Think about how often we see medians in everyday life. Median wage, median population, median home prices, ages, test scores. This is a common thing to want to do. However, if you're an experienced programmer, you see a lot of issues with what ChatGPT recommended. It's not generic, it's a vector, it's integer specific, there's performance issues, there's correctness issues. Wouldn't we love to have an algorithm that works for the new, or even the average, or even, dare I say, to this crowd, the professional? There's a big opportunity here. As Roy mentioned yesterday, speaking of Alex Stepanov, we have found a rabbit. We have an opportunity here to establish an algorithm that thousands, tens of thousands of software developers can use on a regular basis. My name's Pete. I'm going to take you on a journey from the code you just saw to perhaps a generic algorithm that might even be good enough that we could standardize it. You're going to see lots of cringy things as we go on this journey. But that's okay. I invite you to withhold your judgment and your questions until we get to the end. Our goal is something like this. Works for any sortable range, const expr, all the things. And I wonder if we could get it to be really fast. Maybe order n. That's ambitious, but perhaps. As a stretch goal, if you look at range algorithms today, or any algorithms in the standard library, you will see that they support parallelism through execution policies, custom predicates so we can do custom comparisons, projections. Maybe we can even get here. So let's take a crack at it, one step at a time. Here's what we started with. The first problem that I immediately see is this doesn't work if the container is empty. We access vector of 0, undefined behavior. Okay, so what are we going to do? Return an error code, maybe? But we're always returning an integer. An error code of 0, that's a valid median. So is -1. In fact, all integers are valid return values. So returning a flag doesn't sound great. Let's just punt for now, and we'll throw an exception. This is a little cringy. We'll come back to it. Okay, so let's test this out. It now works for 0. It works for 1, an element of 1. What happens if there's 2 elements? Let's say a 4 and a 5. Median of 4 and 5. Right now, it returns the element at position 1, so it will return 5. That doesn't seem quite right. Should it return 4? Wikipedia to the rescue. If the data set has an even number of elements, median is usually defined to be the arithmetic mean of the 2 middle values. So if we have 4 and a 5, those 2 elements, we should return 4.5. Okay, we can do that. So now if we have an odd number of elements, like 1 or 3, there is only one middle element. We'll just return that. And if we have an even number of elements, we'll take the sum of those 2 middle elements, divide by 2. Now that half minus 1 should give you a little pause. Anytime we're subtracting a value from an index, there's a potential that we're accessing a negative index. But you can see by inspection, by the time we get to that last line, there's always at least 2 elements in the container. And so if there's only 2 elements, for instance, half minus 1 is 0. We're all good. But you may have seen another issue. So if we add 4 and 5, we get 9. Integer divide by 2, that's going to give us 4, not 4.5. We want to return a floating point value. Right now we're returning an integer. So let's change this to return a floating point value. Okay, great. But we still have a math problem. Can you spot it? That integer addition, when we add those 2 middle values, when we have an even number of elements, is a signed integer addition. It could overflow. That would be undefined behavior. So that's a problem. Fortunately, in C++20, there's a solution for this. And you should all know about this function and have it in your toolbox. It is called midpoint. And it does the right thing. It handles overflow correctly. And it handles it correctly for any arithmetic value and even pointers. Okay, we're making good progress here. And maybe now it's time to ask about performance. So consider this code for a moment, just by inspection, and think to yourself, what are you concerned about? Sort. However, we should always run our profiler. But when we do run our profiler for any large number of elements, sort is the bottleneck for this function. It's a n log n operation. So let's think about this for a moment. Now, remember, all we're trying to extract from this huge container is the median value, one value, maybe 2. So all we want to know is the position of 1 or maybe 2 elements in that huge, potentially huge list. And it turns out there is already an algorithm for this. It's been living under our noses for years, decades, and it is called nth element. Nth element should also be in your toolbox of algorithms. Nth element answers the question, if this container was sorted, what element would be at position n? It also permutes the container, but it doesn't sort it. It just partitions it. And get this, the best news ever, it runs in average linear time. Amazing. It's typically implemented using intro select, very good algorithm to know. The other thing we've had to change here is previously we've been using indices, but nth element is a standard algorithm. It requires iterators. So now we've switched to use iterators. When we extract mid, it is the iterator pointing to the middle of the container. And then we ask nth element, what position, if this container was sorted, would be at what this iterator is pointing to. It makes sure that the value there is exactly the same value that would be there if the whole thing was sorted. Great. That's pretty amazing. Now, when there's an even number of elements, we want the position of two iterators to be correct, the values there to be correct. So we access mid minus 1. But remember that I said that nth element does not guarantee the container is sorted. In fact, it's not likely to be sorted. It's only partitioned. So things in the first part of the container will be less than or equal to the value at mid, and the other side of the container will be greater than or equal to mid, but we have no guarantee about the order of those elements. So when we access whatever happens to be at mid minus 1, who knows what it is? We only know that's less than or equal to the value of mid. So this code is incorrect. We can fix that by calling nth element a second time if we have an even number of elements in the container. We also have to do something very important. We have to save off the value we get from the first call to nth element, store that in mid value, because when we call nth element for the second time, it invalidates those iterators that we've already extracted. It feels to me like maybe we're doing a little more work than we need to. Wouldn't it be great if there was an algorithm, let's say nth elements, where you could pass two n values? Such an algorithm, however, does not currently exist, but there is a faster algorithm we could use to get that second middle element. And it's an algorithm that will get the biggest value in a range. And that's really what we want. The biggest value in that lower section of this container would be the element that is right next to mid. And that algorithm, that should also be in your toolbox, is called max element. So we can extract out that lower portion of the range, run max element on that half of the range, and that will give us the value that would be next to mid neighbor. Great. Now we've got really good performance. We have nth element on average linear time. We have max element linear time as well, but only on half the container. And you may be wondering, well, what does our performance look like now if we compare with what we started? So I ran the experiment on this laptop with a vector of 10 million integers. The version that calls sort that we started with takes about a second. So on average, 972 milliseconds. The version we've ended up with at the moment, only 89 milliseconds. So a 10x performance improvement. That's really good. But we're not done yet. This is not truly a generic algorithm. It's only working for vector containers. It's only working for integers. What about arrays or decks or any random access container, maybe one that you write yourself? It should work for those too. So let's see if we can make this a generic function. That would mean we need to templatize it. And I want you to notice that already we're calling a bunch of generic functions. We're calling empty and begin and nth element and max element. So it turns out that writing the templatized version is extremely easy. All we need to change is that first line. So now we've templatized on the container. I've changed the V's from vector to C's for container, and that is all that's changed. All of a sudden, we have a generic algorithm that should work for any sortable container. Is it reasonable to want to call median on a list of strings? I think so. Or dates. Certainly dates. Median date. What about employees when you have some sort of comparison function like performance or tenure? And yet, the return value of this function is double. So if we try using it on strings, it's not going to work. We'll get a compiler error because we're trying to convert those strings to doubles. So what do we do in this case? It's time to think about how other algorithms work. Think about the find algorithm. It doesn't return a value. It returns an iterator. That gives us a clue. Maybe we should be returning iterators. So all I've done now is changed from returning a value to returning the iterator. If we have an odd number of elements in the container, we can just return the iterator to the middle element. All good. If we have an even number of elements, then there's two middle elements. What do we do now? Do we return one or the other? Both? Maybe both. So here's a version that returns iterator pairs. In the case where there's an odd number of elements in the container, we return a pair that both point at the same middle element. And in the even number case, the two middle elements. And this is kind of cool. Like if we have an arithmetic type, in both cases, we can add up the types and divide by 2 and get the right results. We're requiring the caller to do a little more work. They have to check those iterators, make sure they're not end, for instance, for empty containers. But we're used to doing that already. And now we work for anything that is sortable. We work for dates. We work for strings. We work for complex numbers, employees. And I just mentioned empty containers. I'm not going to go through the details, but by inspection, we can guarantee that this code, if is called with an empty container, will return two end iterators. So we can get rid of the empty check. This is looking pretty good. We have a generic algorithm that's quite simple. So that's usually a sign that we're on the right track. But we're not there yet. Let's recall our goal. We wanted to get to something like this with constraints on the range, const expr. So, what if we just change our signature to match this? Now we've got range in place of container, RG in place of C, and that's all that changed. Nth element and max element are already const expr, and so we can make this function const expr, and everything works the way we want it to. Okay, now what about our stretch goal? This, unfortunately, is not easily obtainable if we want to align to C++20 or C++23. Execution policies, which allow vectorization and parallelization of algorithms, are only supported today by non-range-based algorithms, algorithms where you pass begin and end. Projections, on the other hand, that's new with range-based algorithms, but not supported by iterator begin-end-based algorithms. So if we want to align, currently we have to have either both or one or the other. Let's assume, for the sake of argument and for the sake of time, that we wanted to have execution policy supported. What would that look like? It would look like this. So this is the kitchen sink version. We've thrown just about everything at it that we could possibly throw. If nth element and or max element support parallelization, and they both take policies, execution policies, you'll get those benefits automatically. However, we unfortunately now can't be const expr because execution policy overloads aren't currently const expr. Now we're getting into the weeds of kind of modern C++ and issues that we're facing. But this is a pretty amazing algorithm that we've come up with. One more thing we can do, we can provide better error messages to our customers with some requirements using concepts. So I'm going to add just one more line here. That's the requires that the range be sortable. So now if we pass something that's not sortable into our algorithm, we're going to get a nice error message. Okay, we have come a long way. We have a generic algorithm. It works for any range that is sortable. It's linear time on average, which was our goal, which we thought was pretty ambitious. It fits on one slide, which is pretty incredible in and of itself. But we're not done yet. We need to consider the caller of this function. That's the most important thing. Like, we can write the most beautiful algorithm in the world, but if it's hard to use, that's a problem. How's this going to be used in the real world? And it turns out that using this function as it's written is quite complicated. So in the original version that our new programmer wrote, that was easy to use. You called median, you got the value, done. Okay, it wasn't correct, it didn't work for sortable, every sortable container, it wasn't generic. But our proposed version, we have iterator pairs that we have to deal with. What do we even call them? Those two middle elements, I'm calling them mid-low and mid-high, but that's kind of confusing. We have to compare against end if we have an empty container. And now we've pushed using midpoint to the caller, and the likelihood that somebody's going to use the right thing and avoid integer overload for arithmetic types is pretty low. So how can we make this better? And I want to credit STL from Microsoft, who provided me some insight to take this to the next level. And his proposal was, we should tuck away this result in a little intermediate class that hides some of these details. So here's the median result class. I'm not showing the whole thing, but this is essentially it. It has some iterators in it that we can access. If we have an arithmetic type, it has a value function that will compute the median properly using midpoint. And it's templatized on floating point values, so you could use float, double, whatever. Then all we have to change, back in our kitchen sink version, is we return the median result. And we pass in the iterators that it captures. So now the calling code looks quite a bit easier. We can get the middle value by calling median.value. And we've got a standard optional here. So we use what we're used to with standard optional. Is there a value there? If there's not, it was probably an empty range. And if there was a value, we can just do startup middle to extract the middle element. It's going to call midpoint for us automatically for arithmetic types, all good. And I showed a one-line version to do it all in line. Pretty amazing. So, some takeaways. A generic version of median is not only possible, I think it's really valuable. And I think it's something that we should do. We can use the existing algorithms to implement it very efficiently, much more efficiently than what the AI of today might recommend to the average programmer. Works for any sortable range, supports all the wonderful things that we have come to know and expect with algorithms. Hide away that confusing iterator pair in this little intermediate class, and do the right thing by calling midpoint. There's still some problems here, though, and I think it's important to say that we're not done yet. It's very surprising to a caller that median would permute the container. That's unexpected. If you call median, you kind of assume, well, it's just going to find the median, right? Without making any changes. But it does permute the container. So that would have to be something that we documented very clearly, because it's the only way for us to get the performance that we want. There are performance opportunities we've left on the table. For instance, if there was an nth element, we could get much better performance. It's not necessarily a bad thing. We want to give implementers the opportunity to provide those sorts of performance improvements. It's also not as flexible as we might have thought. You know, it's generic, works for any sortable container, any contained type that can be sorted, and yet I can imagine a version of this that does quartiles, right? A median is just an example of getting one sorted element from the middle, but we might want to get it at every quarter. We might want to get the P95 or the P5. So it's not as flexible as maybe we thought that it might be. The usage pattern is also still a little squidgy with that intermediate type. What else? You've probably seen some things here that you might change. So some next steps. I think the next step is to make a version of this that would work for any percentile range. Perhaps it's called percentile, for instance, and median would be a specific implementation that under the cover is called percentile. It turns out, this is great news, there's a proposal for multi-nth element that would do exactly what we want. You could pass in multiple n's. Beautiful. There's also some existing statistics proposals. However, those are only for sorted ranges and running medians. But it would be good to align whatever those algorithms look like with what we have proposed here. And there is no proposal. It hasn't been written yet. So that needs to happen. So we're not at the end of the journey. We're somewhere in the middle of the journey, maybe even the beginning of the journey, because standardization can take years. And it's important to reflect on what we've learned. Not surprisingly, AI is not always your friend. You knew that already, but it's good to be reminded. Making algorithms generic is a pretty powerful thing to do, particularly for things like this, median, a very popular thing that people want to do all the time. We don't have an implementation in the standard, and there should be. It's also challenging to make them generic. And just when you think you've cracked the nut, you find another problem. Rewarding? Perhaps. Maybe we can get there. You've learned some new functions. You've learned about midpoint. You've learned about nth element, max element. Good to have those algorithms in your toolbox because they're very important and very useful. Caller is king. Never forget that. Like, it's not enough to create an algorithm that's useful unless it's useful to all the callers and easy to use. And hopefully, I've convinced you that median should be standardized. So, I used to work at Microsoft many years ago. There was always a call to action slide. This is your call to action. Do you have a better approach? Let's talk. Do you have a suggestion? Let's talk. Are you concerned about anything that I've shown here? And you're like, Pete, wait a minute, that's totally off base. Or we could tweak this and make this even better. Let's talk. Do you want to help with a proposal? Let's talk. Would you like to review a proposal? Let's talk. You get the idea. If this is something that you're excited about, that you're interested in, I want your support. I want you involved. We have come to the end of our time together. I realize there's no time for questions, but I will happily be up here at the podium to chat. So I will close by saying thank you.